Section A, angles defined.
Okay, an angle is two rays that share the same endpoint. Let's take a look.
At point A, the angle is formed by rays AC and AT, which form the sides of the angle. They share endpoint A, which is the angle's vertex. Point S is an interior point because it's inside the angle, and point H is an exterior point because it's on the outside. This angle can be named four ways: angle A, angle CAT, angle TAC, or just angle 1. Notice that the vertex, A, is always listed in the middle of both the CAT and TAC notations.
Look at these two angles here, YAP and DOG. The measure of angle YAP is 60 degrees. We see that the measure of angle DOG is 60 degrees also. So as we said earlier, two angles that have equal measures are congruent. So the measure of angle YAP is equal to the measure of angle DOG, and angle YAP is congruent to angle DOG.
YAP and DOG are what we call acute angles. Acute angles measure less than 90 degrees.
A right angle measures exactly 90 degrees. We designate a right angle by putting a small square at the vertex of the angle. An obtuse angle measures more than 90, but less than 180 degrees. A straight angle measures exactly 180 degrees. Note that a straight angle looks just like a straight line. We told you geometry is mystical.
Now that we have single angles down, let's look at some pairs of angles that have special names.
First, adjacent angles. Adjacent angles are coplanar angles, you know, the kind that lie in the same plane. They have a common vertex and a common side. Since the adjacent angles are touching and not overlapping, they have no common interior points.
Next, let's look at complementary angles. Complementary angles are two angles whose measures add up to 90 degrees, like angles Y and O here. The measure of angle Y is 33 degrees, and the measure of angle O is 57 degrees. If we add the measures of angle Y and angle O together, we get 90 degrees, the measure of a right angle. So angles Y and O are complementary.
Supplementary angles are two angles whose measures add up to 180 degrees. Like angles D and A. The measure of angle D is 99 degrees, and the measure of angle A is 81 degrees. We add the measures of angle D and angle A together for a total of 180 degrees, which is the measure of a straight angle. So, angle D and angle A are supplementary.
Notice that complementary and supplementary angles do not need to be adjacent. It's all about their measures. They could be lying around just about anywhere, as long as their measures add up just right.
Next, vertical angles. Vertical angles are two angles that occur opposite each other when two lines intersect. When these two lines intersect, they form four angles. In this diagram, angles 1 and 2 are vertical angles. So are angles 3 and 4. The cool thing about vertical angles is that they're congruent. So if you know the measure of one, you also know the measure of the other.
For example, if we're given the measure of one of these angles, we could figure out the other three. Watch this. If angle 1 is 55 degrees, then angle 2 is also 55 degrees, because they're vertical angles. See that angles 1 and 3 are supplementary angles? Together, their measures will add up to 180 degrees. We know the measure of angle 1 is 55 degrees, so angle 3 measures 180 degrees minus 55 degrees, or 125 degrees. Angle 4 also measures 125 degrees because angles 3 and 4 are vertical angles. So we've got all four.
Vertical angles are really powerful tools that we'll use a lot when we get to proofs. But before we get to proofs, let's look at some other angle stuff.
An angle bisector is a ray that splits an angle smack dab in the middle, forming two congruent adjacent angles. Here, ray QR bisects angle SQT. Angle SQR is congruent to angle TQR. Note the curve symbol inside of each of the angles. If there's a slash in each one, then that means the angles are congruent.
And finally, perpendicular lines are intersecting lines that form right angles. Rays and segments can also be perpendicular. Here we have two perpendicular lines, L and M. So all four angles, D, O, G, and S, are right angles. When we write that two lines are perpendicular, we use a special symbol. L is perpendicular to M.
Now that we know all about angles and their special names, it's time to get theorem-y about angles.
Section B, angles and their theorems.
Before we get into angles and their theorems, we need to review some algebraic properties that we'll be using in a few minutes. These are really useful because these properties work for equal and congruent statements.
Let's start with the reflexive property. The reflexive property states that a value is equal to itself. You know, like when you look into a mirror and you see your own reflection.
In geometry, we'll use the reflexive property to state that an angle or segment is congruent to itself. This may sound kind of obvious, but it'll actually come in very handy in geometry. You'll see.
We'll also be using the substitution property. Let's say we have two statements. The measure of angle 1 plus the measure of angle 3 equals 180. And the measure of angle 1 is equal to the measure of angle 2. By using the substitution property, we can switch two values that are equal, the measure of angle 1 and the measure of angle 2 in our first statement. So, the measure of angle 2 plus the measure of angle 3 equals 180. Switching the values of the measure of angle 1 and the measure of angle 2 is substitution.
All right, now let's look at the transitive property, which says that if A equals B and B equals C, then A equals C.
Here's an example of the transitive property. Say that you get the same haircut as your friend, and your friend has the same haircut as the monkey. Then according to the transitive property, you have the same haircut as the monkey. But don't worry, it looks good on you.
Now that we've got those properties of algebra under control, we're going to get into the angle-related theorems. These are important theorems we'll be using in later proofs, so be sure to go back and review this section to make sure you get them down.
Theorem. If two angles are the complements of two congruent angles, then the two angles are congruent.
You see how that works? If angle 1 and angle 2 are the complements of angle 3 and angle 4, and angle 3 and angle 4 are both 60 degrees, then angle 1 and angle 2 must be 30 degrees. So they're congruent. This works the same way with supplementary angles. Here's that theorem. Theorem. If two angles are the supplements of two congruent angles, then the two angles are congruent. Now here's the theorem about angle bisectors.
Theorem. Every angle has exactly one bisector. Remember how we said that each segment has exactly one midpoint? Well, the same is true of angle bisectors. So as angle CUT is bisected by ray UP, we get two congruent angles, CUP and TUP.
When do we get to prove a theorem?
Real soon.
Now, I am tired of this inactivity, okay? I got cabin fever, all right? I'm young, I'm alive.
Okay, we'll do a proof. But first, there's some things you need to know. A proof is just a series of logical steps that prove the truth of a theorem. Before we prove anything, we're given some information. We'll use this given information to set up our theorem, which in this case proves a property of vertical angles we're already familiar with.
Our theorem says that two vertical angles are congruent to one another. So, given that angle 1 and angle 2 are vertical angles, we'll prove that angle 1 and angle 2 are congruent. And in a broader sense, we'll prove that two vertical angles are congruent.
One more thing. As we go through the process of proving theorems, we'll set up a proof table. We'll put statements on the left and reasons on the right. You may not understand why we do each step right now, but don't worry, it'll all make sense in the end.
Here we go. We'll begin by stating our given information. Angle 1 and angle 2 are vertical angles. No big whoop. Our second statement is the sum of the measures of angle 1 and angle 3 equals 180. And the sum of the measures of angle 2 and angle 3 equals 180. How do we know this? Because angle 1 and angle 3 form a straight angle, which measures 180 degrees. Ditto for angle 2 and angle 3. Our reason, this is the definition of a straight angle.
Next, we'll set the sum of the measures of angle 1 and angle 3 equal to the sum of the measures of angle 2 and angle 3. Our reason is the substitution property, because, as we saw in step 2, each side of the equation equals 180.
Our fourth step is setting the measure of angle 3 equal to the measure of angle 3. Our reason? It's the good old reflexive property.
Now that we've established that the measure of angle 3 is equal to itself, our next step is to subtract the measure of angle 3 from each side. Our reason here is just plain old everyday algebra. Once we do that, we're left with the measure of angle 1 equals the measure of angle 2. And because of the definition of congruent angles, we know angle 1 is congruent to angle 2. So we've proved the theorem that says vertical angles are congruent.
We all enjoy proving theorems. Now, don't forget all the tools that you have at your disposal when doing proofs. There's given information, definitions, postulates, algebra, algebraic properties, and previously proven theorems.
Proofs are an excellent example of both inductive and deductive reasoning. Setting a goal for a proof is an inductive process, and because we support each step by reason, we're thinking deductively. So our little brains are really working. We'll look at some more proofs in a few minutes, but for now, it's time for a little look back.
An angle is formed by two rays that share an endpoint. Adjacent angles are coplanar angles that share a common vertex and side. Complementary angles are two angles whose measures add up to 90 degrees. Supplementary angles are two angles whose measures add up to 180 degrees.
Vertical angles are congruent. An angle bisector is a ray that splits an angle smack dab in the middle. Perpendicular lines are two lines that form right angles where they intersect. And a proof is a series of logical steps that prove the truth of a theorem.
Section C, parallel lines and angles.
As we discussed earlier, parallel lines are two or more lines that are contained in a plane and never touch.
The parallel postulate is one of the most important postulates in geometry. It says, given a line, L, and a point, P, not on that line, there's exactly one line, M, through the point P that is parallel to line L.
Did you get that? So I've got a line and I've got a point, all in the same plane. The parallel postulate says that there's only one line going through the point that's also parallel to the line.
Although an infinite number of lines could go through point P, only one runs parallel to line L. This is what all of Euclidean geometry is based on. Now that we're familiar with the parallel postulate, we can discuss some special facts about parallel and not parallel lines and the angles formed when an intersecting line comes to town.
When two lines are cut by a line, we call this intersecting line a transversal. When the lines are cut by the transversal, 8 different angles are formed. See them all there? There are 4 different ways to categorize these angles. The most general way is corresponding angles. Angles 1 and 5, 2 and 6, 3 and 7, and 4 and 8 are corresponding angles because they're in the same position on either line. They correspond to each other.
Angles 3 and 5 and 4 and 6 are alternate interior angles. They're all interior angles because they're between the two lines. The pairs we mentioned are alternate interior angles because they are on alternate or opposite sides of the transversal.
Angles 1 and 7 and angles 2 and 8 are alternate exterior angles. These guys are all exterior angles because they are on the outside of the lines. Again, the pairs are alternate exterior angles because they are on opposite sides of the transversal.
Angles 3 and 6 and 4 and 5 are same side interior angles because, well, the pairs are all interior angles on the same side of the transversal.
Now that's a lot of angles for just 2 lines and a transversal, but it's not too tough. Now let's change the situation a little. We have the transversal intersecting a pair of parallel lines. Let's check out the corresponding angles.
What if we measure the corresponding angles in this diagram? Look specifically at angles 1 and 5. They seem to be congruent, right? What about angles 3 and 7? They seem to be congruent as well. So using inductive reasoning, we'll assume the following 2 statements in the form of if P then Q. Our first statement is, if 2 parallel lines are cut by a transversal, then the corresponding angles are congruent. And in the form of if Q then P, our second statement is, if 2 lines are cut by a transversal and the corresponding angles are congruent, then the 2 lines are parallel.
We'll use our deductions here to form a double fact statement that can be summarized as the corresponding angle postulate. Lines are parallel if and only if corresponding angles are congruent. We'll accept this as a postulate because we don't have enough information in our earlier postulates and theorems to prove it yet.
So what we've done is we've used inductive reasoning to develop the corresponding angle postulate. Once we accept this postulate, we can prove theorems about alternate interior angles and about alternate exterior angles.
I accept it.
Okay, great. Let's look at alternate interior angles. The theorem we want to prove is lines are parallel if and only if alternate interior angles are congruent. We need to prove each statement separately because this, like the corresponding angle postulate, is really two statements in one. The first statement, the if P then Q part, is if a transversal cuts two parallel lines, then the alternate interior angles are congruent. The second statement, if Q then P, is if a transversal that cuts two lines creates congruent alternate interior angles, then the lines are parallel. Let's do a proof.
We'll start with the first statement we just identified and prove that, then move on to the second statement. The first statement was, if a transversal cuts two parallel lines, then the alternate interior angles are congruent. So given that the lines L and M are parallel, we'll prove that angle 3 is congruent to angle 5. Okay, let's set up our proof table. First, we state our given information. Line L is parallel to line M.
For our second step, we state that angle 1 and angle 5 are congruent. We do this because of the corresponding angle postulate we just talked about. Remember the corresponding angle postulate? It says that corresponding angles, like angles 1 and 5, are congruent.
In our third step, we state angle 1 is congruent to angle 3. The reason we do this is because of the theorem we proved earlier. Vertical angles are congruent, which says, well, that vertical angles, like angles 1 and 3, are congruent.
Our final statement is angle 3 is congruent to angle 5. We can say this because of the transitive property.
In our theorem, we've shown that angle 1 is congruent to both angle 5 and angle 3. Because of this, we can use the transitive property as our reason to say that angles 3 and 5 are congruent to one another. And since angle 5 and angle 3 are congruent alternate interior angles, we've proven our goal. Alternate interior angles are congruent.
Before we go on to the second part of our theorem, notice that we'll be proving the converse of the statement we just proved. And notice that as we prove this second part, we'll apply much of the same reasoning we just used.
So we're going to prove the converse of the alternate angles are congruent theorem, which states the transversal that cuts two lines creates congruent alternate interior angles, then the lines are parallel. To prove our theorem, we're given that angle 3 is congruent to angle 5. We need to prove that lines L and M are parallel.
Let's set up our proof table. Our first step is to state our given information. Angle 3 is congruent to angle 5.
Next, we state that angle 3 is congruent to angle 1. We can do this because angle 3 and angle 1 are vertical angles, and vertical angles are congruent.
Our third statement is angle 1 is congruent to angle 5. This is true because we're applying the transitive property to angle measures.
Notice that we could not have entered corresponding angle postulate as our reason in step number 3. At this stage of the proof, we hadn't proven that corresponding angles are congruent. We do not yet know if the lines are parallel. This is what we're trying to prove. So, be careful with the postulates you start throwing around. That's it.
However, now we know that the corresponding angles are congruent, so it's time to use the corresponding angle postulate. Line L is parallel to line M because of the corresponding angle postulate, and we're done.
So, we've proven each half of the alternate interior angles theorem. Now we can yell from the mountaintops that lines are parallel if and only if alternate interior angles are congruent.
Moving right along, the alternate exterior angle theorem states that lines are parallel if and only if alternate exterior angles are congruent. We won't prove the alternate exterior angle theorem because it's so similar to the alternate interior theorem, and we wouldn't want to cover this same old territory again. So let's check out the same side interior angle theorem. It's different. How different? Let's take a look.
Remember what same-side interior angles are? They're these guys right here. Looking at the diagram, we can see that these angles aren't congruent. It looks like the supplementary, doesn't it? We'll test our observation by proving this theorem. Two lines cut by a transversal are parallel if and only if same-side interior angles are supplementary. Like the if and only if statement we just proved, we know that this is really two statements in one. The first statement, the if P then Q part, is if a transversal cuts two parallel lines, then the same side interior angles are supplementary. Let's go ahead and prove this theorem. We'll get to the second part in a minute.
Given that line L is parallel to line M, we want to prove that angles 4 and 5 are supplementary. Okay, let's set up our proof table. Our first step is to state our given information. L is parallel to M.
Next, we state that angle 1 is congruent to angle 5. Our reason is the corresponding angles postulate.
Step 3 is the sum of the measures of angle 1 and angle 4 equals 180. We know this because of the definition of a straight angle.
Step 4. Because angle 1 is congruent to angle 5, we use substitution as our reason for stating that the measure of angle 4 plus the measure of angle 5 equals 180.
Step 5. Two angles whose measures total 180 degrees form supplementary angles, and so angle 4 and angle 5 are supplementary angles. We've proved what we set out to.
So, we've proven half of our proof. Remember, we're proving an if and only if statement, so we must proceed both forward and backward. So, the second statement of the proof is the reverse or the converse of the first.
In the form of if Q then P, our converse statement is, if a transversal that cuts two lines creates supplementary same-side interior angles, then the lines are parallel. So, given that angle 4 and angle 5 are supplementary, we'll prove that L is parallel to M.
Our first statement is our given information. Angle 4 and angle 5 are supplementary.
Our second statement is the sum of the measures of angle 4 and angle 5 equals 180 because of the definition of supplementary angles.
Next, we'll state that the sum of the measures of angle 4 and angle 1 equals 180. This is the definition of a straight angle.
In our fourth step, because the equations in step 2 and 3 equal 180, we can set the two equations equal to one another. The sum of the measures of angle 4 and angle 5 equals the sum of the measures of angle 4 and angle 1. This is possible because of the substitution property.
Next, we can drop like terms, the measure of angle 4, on both sides of the equation. Thanks to algebra, this leaves us with the measure of angle 5 equals the measure of angle 1. This also means that angle 5 is congruent to angle 1 because of the definition of congruence.
Our final statement is L is parallel to M. How can we say this? Well, now that we've got angle 5 congruent to angle 1, we can use the corresponding angles postulate.
So, we've proven the same-side interior angles theorem. Lines are parallel if and only if same-side interior angles are supplementary. Now, we've made it to the end of the section. Want to take a look back?
You got it. The parallel postulate is one of the more important postulates. It says that for any line L and point P not on line L, there's exactly one line M through point P that runs parallel to line L.
When a transversal cuts two lines, 8 angles are formed. We categorize them as corresponding angles, alternate interior angles, alternate exterior angles, and same-side interior angles.
The corresponding angle postulate says that lines cut by a transversal are parallel if and only if corresponding angles are congruent. The alternate interior angles theorem states that lines cut by a transversal are parallel if and only if alternate interior angles are congruent.
Likewise, the alternate exterior angles theorem states that lines cut by a transversal are parallel if and only if alternate exterior angles are congruent. The same-side interior angle theorem says that lines cut by a transversal are parallel if and only if same-side interior angles are supplementary. That's it.
Quiz 2.